Chapter 6 takes our idea of dot product and generalizes it to what's called an inner product. Consequently, we can take our idea of vectors and define different ideas as vectors, kind of like what we did in Chapter 5 with our vector spaces. So on this first page, I have all the vocabulary words. I want to focus on a couple that are more specific. For example, the idea of a weighted inner product is when you take something like u comma v as an inner product. But now we want to apply weights to it. So this would be like W1, U1, V1, plus W2, U2, V2. Or those are weights. And basically you create that by doing something like U comma V is actually equal to AU comma AV. And we can rewrite that as AU transpose AB. And A is defined as a matrix involving the weights. It's a diagonal matrix where the elements in the diagonal are square root of W1, square root of W2, so on and so forth. Coordinates relative to a basis, we can now use our inner products to define coordinates relative to the basis. Orthogonal and orthonormal vectors were also defined using Gram-Schmidt orthogonalization, so I will do something with that. W_perp was basically all the vectors that were perpendicular to the vectors defined by W. Normal equations and orthogonal projection matrices where our least squares approximation idea came up. And consequently, we had something called QR decomposition and orthogonal matrix. So an orthogonal matrix is something like Q, such that Q transpose Q equals I. This consequently created a couple of other properties. For example, Q transpose then has to equal Q inverse. And another useful one is that the determinant of Q has to equal plus or minus 1. And then we also had what was called a change of basis matrix. So first I'm going to start with our inner product properties. Basically, you can define a set of vectors with an inner product definition as an inner product space if all four of these properties are satisfied. So I have just one example to show you how these properties work. F of x and g of x are continuous functions on the interval -1 to 1. Typically, we define this as an integral for f and g, but I want to show you why if we try to use our standard definition of inner product, it doesn't work and it doesn't satisfy those four properties. So let's go through each one of these. First of all, if you have f comma g, I want to show that equals g inner product f. But that kind of makes sense because f comma g would basically be f of -1 times g of -1 plus f of 0 times g of 0 plus f of 1 times g of 1. But because multiplication is commutative, that would be the same as g of -1 times f of 1, -1, plus g of 0 times f of 0 plus g of 1 times f of 1. So obviously the commutative property holds. Now, if I do something like a scalar, kf comma g, if I were to rewrite this, this would equal kf of -1, g of -1, plus kf of 0, g of 0, plus kf of 1, g of 1. But since k is just a scalar, I could factor it out of each of these terms, and I have k times f of -1, g of -1, plus f of 0, g of 0, plus f of 1, g of 1. And this would equal k times the inner product of f and g. And you can imagine I could put the k in the other one, and this would also equal f times f inner product kg. So that property is satisfied. Now let's check the distributive one. So that would be f comma, let's say g plus h, if I had an h as another continuous function. So this would equal f of -1, g of -1, plus h of -1, plus f of 0, g of 0 plus h of 0, plus f of 1, g of 1 plus h of 1. But again, we can use a distributive property for this, so this would be f of negative 1, g of negative 1, plus f of 0, g of 0, plus f of 1, g of 1, plus similar ones for h. So this would equal the inner product of f and g plus the inner product of f and h. So that leaves us just the last one that needs to be checked. The last one says f comma f has to be greater than or equal to 0. Well, this is true because f comma f is equal to f of negative 1 squared plus f of 0 squared plus f of 1 squared. And since these are all squared entities and they're being added, this has to be greater than or equal to 0. But the last property, f of f inner product f, equals 0 would mean f of negative 1 squared plus f of 0 squared plus f of 1 squared is equal to 0. But this does not imply that f has to equal 0. This only implies that f of negative 1 and f of 0 and f of 1 equals 0. But since f is a continuous function, I could have a continuous function where f of negative 1, f of 0, f of 1 are all equal to 0, and f of x itself is not equal to 0. So since this is not satisfied, this is not an inner product space. At least using this definition that we have here. So what I'm going to do next is a proof using all the inner product properties that we have. I'm going to start with c of x, or cx plus y, quantity squared, and basically use our definitions of inner product properties to put this together. So cx plus y magnitude squared is basically equal to cx plus y, inner product cx plus y. But again, since inner product properties are distributive, I can rewrite this as cx comma cx plus cx comma y plus x or y comma cx plus y inner product y. And since c is a scalar, I can factor that out and make this c squared x comma x plus cx comma y, because there was only one c factor there, plus c y comma x plus y comma y. Anything inner product itself is equal to its magnitude squared, so this is the same as c squared magnitude x squared. X comma y and y comma x are equal to each other, so this is the same as 2c x comma y plus magnitude y squared. And we finish the proof. Okay, some different examples. Basically, I wanted to highlight some of the definitions we did in this unit and also look at things to be careful of when you set them up. So let's start with these two up here. Okay, so I want to slide these down, and I want to focus on the continuous functions like I mentioned earlier. So first of all, df comma g basically means the Euclidean distance between these two functions. And the Euclidean distance is defined as the magnitude of, in this case, f minus g. So magnitude is basically f minus g, inner product itself. But that's magnitude squared, so we're going to square root that. Now the definition of inner product using continuous functions is an integral. So basically what we're going to have is the integral from 1 to 2 of ex minus cosine x squared, because it's f minus g inner product with itself, dx, and then square root that entire thing. So that would be the Euclidean distance. The cosine of the angle, and notice I never mentioned the angle because you can't really have an angle between two functions. So the cosine of the angle, cosine theta, would be the inner product of f and g over the magnitude of f and the magnitude of g. So again, using our inner product definition for continuous functions over an interval, this would be the interval from 1 to 2 of etx cosine x dx all over the magnitude of f, so that would be the inner product of f times itself, e to the x or e to the 2x dx, square rooted, and the magnitude of g dot itself, so from 1 to 2, cosine squared x dx, and again another square root. So notice that would give a numerical value, which would be the cosine of the angle between f and g. Now, if I have two matrices, if I want to do an orthogonal projection, let's start with the orthogonal projection. Okay, so this would be the projection of A onto B, which is, by definition of projections, the inner product of A comma B all over the magnitude B squared times the vector B. So A inner product B, when you have two matrices, you basically multiply corresponding components and add them up. So in this case, it's going to be negative 2 minus 56 minus 30 plus 12 over the magnitude of B squared, which is going to be each component multiplied by itself, and then squared, so there's no square root involved here. So that's going to be 1 plus 64 plus 25 plus 16 times vector B, which is a matrix, negative 1, 8, negative 5, and 4. So that would be the projection. Now, to find W perp. So we're going to let W represent the space spanned by A and B, and we're going to find W perp. Well, W perp represents all the vectors that are orthogonal to A and B. So basically, I want to set up a system so that these matrices dot something equals 0. To do that, we want to kind of think of them almost as vectors. So I'm going to set this up as 2, negative 7, 6, and 3. And then the other one, negative 1, 8, negative 5, and 4. So I want to imagine I have a vector, x1, x2, x3, and x4. So that if I dot these two together, I would get 0 and 0. Now, a couple of things I want to mention, or actually one thing I want to mention. Since my vectors are represented by matrices, my W perp vector should also be matrices as well. So technically, this is the matrix, x1, x2, x3, and x4, being consistent with how I wrote the other ones. So I'm going to rewrite this in RREF as an augmented matrix, 2, negative 1, negative 7, 6, and 3, 8, negative 5, and 4, augment it with 0, 0. Do a quick RREF on my wonderful calculator, and the RREF is 1, 0, 13 ninths, 52 ninths, and 0, 0, 1, negative 4 ninths, 11 ninths, and 0. So rewriting this into equations, I'm going to have x1 plus 13 ninths, x3 plus 52 ninths, x4 equals 0. I'm going to have x2 minus 4 ninths, x sub 3 plus 11 ninths, x sub 4 equals 0. So consequently, x1 equals negative 13 ninths x sub 2, or x sub 3, plus negative 52 ninths x sub 4. X sub 2 equals 4 ninths x sub 3 minus 11 ninths x sub 4. So my general solution of x1, x2, x3, and x4 is going to be rewritten as negative 13 ninths x3 minus 52 ninths x4, 4 ninths x sub 3 minus 11 ninths x sub 4, x sub 3, and x sub 4. And if I rewrite this as a linear combination of independent matrices, independent vectors, it's going to be negative 13 over 9, 4 ninths, 1, and 0. So this would be one of my basis vectors. And then my other basis vector would be negative 52 over 9, negative 11 over 9, 0, and 1. And so this would be the basis for W perp. The vectors that are orthogonal to the ones given in W. Now, let's do another proof. So, let V be a finite dimensional inner product space over R. Suppose that S1 and S2 are subsets of V. Prove that if S1, so I need to define this for you. This basically means that S1 contains S2. And so likewise, this one means that S2 perp contains S1 perp. Okay. So visually, S1 contains S2. That means basically if this space here is S1, then S1 contains S2, so S2 is somewhere in here. And then vice versa, S2 perp contains S1 perp, so my bigger space this time is S2 perp, and it contains S1 perp. And so what I need to do is prove that if S1 contains S2, then S2 perp contains S1. Sorry, S1 perp. So I'm actually going to do a proof by contrapositive. Proof by contrapositive, so I'm going to show that if S2 perp does not contain S1 perp, then S1 does not contain S2. So basically I'm going to reverse it and use the opposite. Let's start here. We're going to let X be an element of S2 perp but X is not an element of S1 perp. So let's see, S2 perp does not contain S1 perp. So basically I'm going to make sure that X is an element of S2 perp, but since it does not contain S1 perp, I want to make sure that X is not an element of S1 perp. Now I want to show that this produces a contradiction. So if X is an element of S2 perp, then X is not an element of S2. Oh, I need to say something up here before I start. So assume X is a non-zero vector. Because we know the zero vector is always in any combined, in intersection of any vector spaces. Okay. So if X is an element of S2 perp, then X is not an element of S2. And similarly, if x is not an element of S1 perp, then x must be an element of S1. Okay. But if x is an element of S1 and x is not an element of S2, then S1 cannot contain S2. Because if x is not an element of S2, then automatically it cannot be an element of S1 as well. So that's my proof by contradiction. Okay, a process that we talked about in this unit was what's called the Gram-Schmidt orthogonalization process. So I'm going to use this to actually talk about orthogonal vectors, orthonormal vectors, and so on and so forth. This is going to be a fairly long slide. So I have S being defined by three polynomials, Px, Q, and R, and we're going to use a standard inner product for P2 polynomials. We're going to start by creating an orthogonal set of vectors, and then I will orthonormalize them later, and this way I can talk about different coordinates and how to find coordinates relative to our basis set using inner products instead of using an REF. So this is going to take a while. Alright, so let's start with our orthogonal set of vectors. I'm going to let v1 equal the first vector. So 3x squared plus x minus 1. And like I said, I want to make them orthogonal first, so I'll orthonormalize them later when I get to question 3. v2 is going to be the orthogonal complement of the projection of q onto p. So this is going to equal 4x squared plus 2x plus 3 minus the projection of 4x squared plus 2x plus 3 onto v1. 3x squared plus x minus 1. So if I do this, it's going to equal basically 4x squared plus 2x plus 3 minus the dot product between the vectors, and we do that by multiplying the corresponding coefficients. So that's going to be 4 plus 2 minus 3 over the magnitude of the vector that I'm projecting onto, 9 plus 1 times the vector that I'm projecting onto, 3x squared plus x minus 1. So if I substitute all of that into my calculator, I get the polynomial x squared plus x plus 4. So that's going to be my v sub 2. V sub 3, I'm going to do the same thing, except I'm going to have to take the orthogonal complement to two projections. So v sub 3 equals my last vector, x squared minus 2x plus 1, minus the projection of x squared minus 2x plus 1 onto v sub 1, 3x squared plus x minus 1, minus the projection of x squared minus 2x plus 1 onto v sub 2, x squared plus x plus 4. So this basically becomes x squared minus 2x plus 1. If I dot the next two, I get 3 minus 2, which is 1, minus 1, which is 0, which is awesome, so it's already orthogonal to that. So I just got to minus the second one, so this actually comes out 0, which will be 1 minus 2 plus 4, all over the magnitude, which is 1 plus 16, times the vector that I'm projecting onto, which is x squared plus x plus 4. And so if I do all that, I believe I get 5, 6 x squared minus 13, 6x plus 1/3. Now I'm going to rescale this since all I'm really interested in is that they're orthogonal. So I'm going to make this 5x squared minus 13x plus 2. Alright, so a couple of things before I start talking about the coordinate system. First of all, these are orthogonal vectors. So notice if I were to define a matrix Q with these as their column vectors, it would be something like 3, 1, negative 1, 1, 1, 4, 5, negative 13, and 2. And then if I did something like Q transpose Q, I would get the diagonal matrix 11, 0, 0, 0, 18, 0, and 0, 0, 198. So that's one way you can always tell if a set of vectors are orthogonal, is to find them as column vectors, do a Q transpose Q. If it's diagonal, then you know it's orthogonal. And that kind of makes sense because basically what's happening is we're doing V1 dot V1, and so we're getting 11 for that. But if I do V1 dot V2, since they're orthogonal, that's going to be equal to 0. And notice right here, here, and here, all these diagonal elements are basically the magnitude squared of all the vectors that we were looking at. So that was kind of a side note. Now, the coordinates of f of x relative to s sub 1. So those vectors up there are my s sub 1s. Coordinates are basically how much I want to go in each direction of the basis vectors. So they're just numbers. It's like 3 units this way, 7 units that way, negative 2 units this way. And we can do an RAF, but since they're orthogonal, we can also use the idea of projection. So f of x, the coordinates for f of x, would basically be the projection of f of x onto v1, so inner product of that, over v1 squared. Now if you think about it, normally I would multiply this by v1, but like I said, I'm just interested in how many units in the v1 direction I need to go, which is why we don't have this v1 and we have the v1 squared on the bottom. So then the next coordinate would be f of x inner product v2 over v2 squared, and f of x inner product v3 over v3 squared. Now this is relative to s1, so I want to denote s of 1 there, so I know that I'm using a different basis system to put this together. So if I put all those numbers in, this comes out to be, let's see, I think 16 over 11, 2 over 18, and 100 over 198 relative to the basis s of 1. So that's the first one. Now I want to take that same set of vectors and make them orthonormal and show you how that changes the projection when I'm trying to find the coordinates. So fortunately that's not as hard because all I got to do is I got to take the v's and divide them by their magnitude. So let's call them, I don't know, w1. So I'll make w1 equal to 3x squared plus x minus 1. But we're going to normalize it. So this is going to be over the square root of 11. W2 will equal x squared plus x plus 4 over the square root of 18. And W3 will equal 5x squared minus 13x plus 2 all over the square root of 198. By the way, I realized I could have just made this basis vectors 1, x, and x squared. I was just trying to pick something easy to do Gram-Schmidt. Alright, so that would be my orthonormal set of vectors. Now, let's talk about the coordinates of 3x plus 1 relative to this. So kind of same idea. This would be the inner product of g comma w1 over w1 squared. But w1 has a magnitude of 1 because I divided it by its magnitude, so that actually equals 1. So then the next would just be g inner product w2, and then g inner product w3. And this is relative to s sub 2. So if I put all my numbers in, this basically comes out to be 2 over root 11. 7 over root 18, and negative 37, I believe, over square root of 198. relative to S sub 2. Oh, by the way, I forgot to mention. Up here, if I were to define a matrix Q equal to this, W1, W2, and W3 as column vectors, and I did a Q transpose Q here, this would actually equal the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Because W1 inner product itself would be 1, W1 inner product W2 would equal 0. So Q is what's called an orthogonal matrix. So a little bit confusing. Orthogonal matrix actually is made up of orthonormal vectors, not made up of orthogonal vectors. Let's see. Okay, so last thing we did after we did Gram-Schmidt was we talked about what was called QR decomposition. So I want to review QR. Basically, A equals QR. Q is your orthonormal vectors. And then, so in this case, it would be W1, W2, W3, written in column format. R is the upper triangular matrix, basically made up of inner products. So R would be, let's see here, it would basically be my original vectors, which would be like P inner product W1. And then would be, I want to make sure I use the same letters, Q inner product W1 and Q inner product W2. And then over here, this would be R inner product W1, R inner product W2, and R inner product W3. So I'll write the QR decomposition for this one. So Q in this case would be my orthonormal vectors, which are 3 over square root of 11, because they're orthonormal, 1 over square root of 11, and negative 1 over square root of 11. Then W2 is, remember, over root 18. So this is 1 over square root of 18, 1 over square root of 18, and 4 over square root of 18. And then the last one was over the square root of 198, so that would be 5 over the square root of 198, negative 13 over the square root of 198, and 2 over the square root of 198. So that is my orthogonal matrix. This is an orthogonal matrix. So if I did Q transpose Q on that, it would equal the identity matrix. Now R is basically P times W1. So if I take P times W1, I get 3 over root 11 plus 1 over root 11 plus 1 over root 11. 9 over root 11 plus that. So that would be 11 over root 11. So this would equal square root of 11. These are actually 0. And if you took P inner product with W2, you would end up with 3 plus 1 minus 4, which actually does come out to be 0. So kind of a double check there. So now we just want to do Q inner product W1, which comes out to be square root of 11. Q inner product W2, root 18. If you try to do Q inner product W3, you get 0 out of it. And then R inner product W1 is 0. R inner product W2 is 3 over square root of 18. And R inner product W3, I believe, is 33 over square root of 198. And you can always do a double check and make sure with your calculator that this multiplies out to the original A. Because that's the whole point. We're trying to rewrite A as a matrix that is easy to invert, actually as a product of matrices. That's easy to invert, because if Q is orthogonal, Q transpose equals Q inverse, and it's easy to invert an upper triangular matrix because of all the zeros that are involved. Alright, time for another proof. So this one I want to show that if I take the cosine squared of each of these angles, it actually equals 1. So I'm going to start with the left side, obviously, because it's easier to work with here. So cosine squared of A1 plus cosine squared of A2 plus, so if I just use my cosine definition, this would equal, let's see, AI is the angle between U and V sub I. So this would equal U comma V1 squared over magnitude U squared, magnitude V1 squared, plus U comma V2 squared over magnitude U squared, magnitude V2 squared, plus so on and so forth. But V sub I are orthonormal bases, so V1 squared has a magnitude of 1, V2 squared has a magnitude of 1. And if I combine this, I now have U comma V1 squared plus U comma V2 squared plus so on and so forth, all over magnitude U squared. However, since V sub I are orthonormal, this is an extension of the Pythagorean theorem, and equals magnitude of U squared. So think of it as basically you're taking a magnitude because you're projecting onto the x-axis, let's say squared plus the y-axis squared plus the z-axis squared. This was actually a homework problem showing that the top was equal to magnitude U squared. So we end up with this equaling magnitude U squared over magnitude U squared, and this equals 1. You could think this also as your coordinates if you think back to the projection idea that we had earlier. So you could think of this as your x-coordinate being squared plus your y-coordinate being squared plus your z-coordinate plus however many coordinates you have. And so basically you have magnitude squared in the numerator. Alright, now we had 2 more sections in chapter 6. One was on best approximation. So I have here a column space being defined in matrix A. I have B representing a column vector, but if I were to try to REF this, I would actually have no solution. So what we're going to do is find the best approximation of B. We're going to find the best approximation of B defined by the column space of A. And this uses what we call the normal equations. So the normal equations is when you have A transpose AX equals A transpose B. So what I did on my calculator was did A transpose A, and I got the matrix 4, 11, and 10, and 11, 39, and 21, and 10, and 21, and 30. Notice A transpose A is symmetric, equals A transpose B, which came out to be 12, 35, and 37. Solving for x, I can do the inverse of A transpose A, and I get x equals, oh dear, let's see if I can read my handwriting. I think it was 85 over 2, and negative 19 over 2, and negative 53 over 6. Now, x represents the linear combination of the columns of A. So x is actually not the approximation of B. X is just what combinations of the columns of A would represent an approximation of B. So the actual approximation of B is what it would look like on the if I were to use the basis vectors in A. So the approximation of B is actually AX. So AX equals 5, 6, and 10 thirds. Yes, 10 thirds, and 35 over 6. And I'm going to erase this because this looks messy. So let me try again, because these are actually 4 components. So 5, 6, 10 thirds, 35 over 6, and 2. So that is the approximate B in the column space of A. Now, if I were to do B minus AX, I would get a negative 11, 6, 11 thirds, negative 11, 6, and 0, which would be the orthogonal complement of the projection of B onto A. And if I were to take one more step and do the magnitude of B minus AX, the magnitude of B minus AX, which would basically be the magnitude of this vector, would equal 11 root 6 over 6. And this would be the error in approximation. So, if I were to try to draw a visual of all this, and say I have A space represented by A. Let's say I have a vector B that's here that cannot be represented by anything on A. What I'm going to do is a orthogonal projection. So this is my approximate B, which equals AX. This here is B minus AX, which is the orthogonal complement, and so the length of that, the magnitude of that would be the error. And I think that's everything from 6.4. The last section we had, do a proof before I forget. Alright, so we're going to prove an orthogonal projection matrix is symmetric. And I kind of wanted to use this just to remind you what an orthogonal projection matrix is. We have our normal equations. A transpose AX equals A transpose B. We use this to solve for X. So X equals A transpose A inverse A transpose B. Now remember, X was not the projection. The actual projection was AX. So that's going to equal A transpose A inverse A transpose B. So basically the question is, what do I do to B to get the orthogonal projection? Well, I do all this to B. So that's my orthogonal projection matrix. So I want to show that if I did A transpose A inverse A transpose B, or A transpose that entire expression, I should end up with the original thing to show that it's symmetric. So I'm going to use my transpose properties, and remember, if you have a product of matrices and you transpose them, you're going to rewrite them in the reverse. So this is going to equal A transpose transpose, A transpose A inverse transpose, and A transpose. But A transpose transpose is just A. Now, I'm not going to distribute the inverse because remember, A itself is not a square matrix, but A transpose A is a square matrix. So I'm going to use my other property, which says that A transpose A inverse transpose is equal to A transpose inverse. And then we have an A transpose here. Now I can use transpose property with non-square matrices. So the inside becomes A transpose, all that inversed, A transpose. And again, A transpose is just A. So this equals A transpose A inverse, A transpose, which was equivalent to the original. So it is therefore symmetric. And that was all from 6.4. 6.5 was our change of basis matrix. So this was basically if I want to change from one basis system to another without having to go through, I guess, what would be called the standard basis, for example, like our IJK basis as a result. The definition I showed you in class was that you want to basically set it up as mu inverse old. And if I remember correctly, the idea here was basically if you had a new system and then you had your vector relative to the new coordinate system, this should equal your old basis vector relative to the old basis coordinates. So if I were to solve this for the new vector, it would basically equal mu inverse times old times your old coordinate system. And so there's our change of basis matrix. So for this particular problem, the change of basis matrix would basically, let's say, I'm going from B1 to B2. So B2 is my new basis system. So it's going to be 0, 3, 2, 1, 1, 1, 3, 4, 1, inverse, old, negative 2, 7, 4, 3, 1, 2, 1, negative 5, and 1. And so if I multiply that together, I get the matrix 3, negative 5 eighths, negative 3 halves, negative 2, 27 eighths, 11 halves, that is a 27. And 0, negative 1/8, and negative 3 halves. So that would be my change of basis matrix from beta 1 to beta 2. So just to give you an example, the long way and the short way. Let's say I had 2, 5, 4 relative to basis 1. So to change this into our standard basis, I would do negative 2, 7, 4, 3, 1, 2, 1, negative 5, 1, times 2, 5, 4, because that's relative to basis 1. And that would equal 15, negative 1, and 22. And then if I wanted to find that relative to basis 2, basically that means I would have my basis 2, which would be 0, 3, 2, 1, 1, 1, 3, 4, 1. I'm solving for the coordinates relative to basis 2, so this one I'm going to leave empty. That's like my x vector. And I want this to equal 15, negative 1, and 22. So if I solve that using RAF or inverse, I'm going to get my basis 2 vector to equal negative 25 over 8, 279 over 8, and negative 53 over 8. Alright, so that's doing it indirectly. Now, if I do it directly, let's see if we get it the other way. So I want to take my change of basis matrix, which was 3, negative 2, and 0, negative 5/8, yes, negative 5/8, 27 over 8, negative 1 over 8, negative 3 halves, 11 halves, and negative 3 over 2. And if I multiply this by 2, 5, and 4 relative to basis 1, I'm going to cross my fingers and hope that I get negative 25 over 8, 279 over 8, and negative 53 over 8 relative to basis 2. And I should have a basis 2. So that checks out. You can do it indirectly using two systems of equations, or you can do directly using a change of basis matrix. Good luck studying. Let me know if you have any questions, and feel free to stop by my classroom anytime.